For our linear algebra problem, we've got a system of two equations really defining a linear transformation. These two equations, u equals x plus y, v equals 2x plus 3y, really defines a linear transformation, though I'm not using a matrix here. Goal is to solve for x and y in two ways. First with elimination, second with an inverse matrix. And with elimination, you don't have to make an augmented matrix, but you can. If I imagine the u and the v on the other side, write down the coefficients for x and y. And should I write 1 and 1 here? No, because u and v are arbitrary. I'd actually want to do it with an arbitrary u and v. Do my row operations. I will first multiply row 1 by -2. Oops, -2 row 1, add it to row 2 and put the answer in row 2 so that I get a 0 there. That was the reason that row operation was done. 1 times -2 plus 3 is a 1. U times -2 is -2u plus v is -2u plus v. Almost done. Now multiply row 2 by -1, add it to row 1 and put the answer in row 1 so that I get a 0 right there. Row 2 is going to stay as is. The only work you need to do is to figure out what goes there. I'm multiplying row 2 by -1, adding it to row 1. Multiply this by -1, I'll get a 2u minus v. Add it to u, it gives 3u minus v. So it looks like the answer is x equals 3u minus v, y equals -2u plus v. I have solved for x and y as linear functions of u and v. This is another linear transformation. You might call it the inverse transformation. In fact, before I do this with an inverse matrix, let me compose these two functions here and here without thinking about matrices. Let's see what happens. Let me take these two equations and substitute into here. If x is 3u minus v, right here, and I take u and replace it with x plus y, and v and replace it with 2x plus 3y, what happens? U gets replaced with x plus y, v gets replaced with 2x plus 3y. I'm going to end up with something very profound. X equals x. That was supposed to happen. Let's try it with the other one too. Y equals -2u plus v. Replace u with x plus y just like before. Replace v with 2x plus 3y just like before. And I get something profound. Y equals y. That's supposed to happen. When you compose a linear transformation and its inverse like this, you get equations like x equals x and y equals y. Let's think of it in terms of matrices now. So again, my original equations were u equals x plus y, v equals 2x plus 3y. In vector form, that's saying the vector whose components are u and v equals this vector involving x and y. Separate that out as a linear combination of two constant vectors like this. Being a linear combination of a couple column vectors is the same as a matrix times a vector whose components are x and y. This matrix times this vector. Call this A and this the vector x. I could call this the vector u, say. I hope it's not too confusing to use u in two ways and x in two ways. In the lectures, I make them bold-faced, and in textbooks, they're bold-faced. Here's how to solve this with an inverse matrix. I don't emphasize this enough in the lectures. I should have, but I don't. So here's something important. Symbolically, if you've got the equation u equals a times x, to solve for x in terms of u, vector-wise, you multiply, assuming it exists, the inverse of matrix of A on both sides on the left. A inverse U equals A inverse of A times X. I'm assuming the inverse matrix exists. It doesn't always exist when I write this. By the associative property, I can rearrange the parentheses on the right here and say this. And it turns out that the inverse of a matrix times the matrix itself is something called the identity matrix. I is the identity matrix. It's in the 2x2 case, it's got 2 1s on the main diagonal from upper left to lower right and 0s on the off diagonal. And it's called the identity matrix because when you multiply it times an arbitrary vector x, you get that vector x back. This is something pretty important that I don't really emphasize in the lectures like I should have. So what I'm illustrating is that to get x in terms of u, vector-wise, you did that multiplication. But I'm not telling you yet how to find A inverse. I'm not even confirming yet that it exists. How do you find A inverse? With a 2x2 matrix, there's a shortcut. With a 2x2 matrix, let's write down in the arbitrary case here. If you've got an arbitrary 2x2 matrix whose entries are A, B, C, and D, the inverse matrix of that is the scalar 1 divided by A times D minus B times C times a matrix that you can form from the original matrix by swapping the numbers on the main diagonal. The D and the A get swapped. The B and the C do not get swapped. They stay where they are, but you put negative signs in front of them. This is a shortcut trick that works with 2x2 matrices. In the lecture, you'll also learn about how to find this using row operations, but for the purposes of class today, I'm just showing you the trick because it's faster. Are you allowed to use the trick on the exam? If I say you can. If I'm just after the inverse matrix, if I say use row operations to find the inverse matrix, then I'd want you to show that work. But this is a trick. And in the present case, our matrix A from the previous page is this matrix. So A inverse is going to be 1 over A times D is 3, B times C is 2. Oh, I guess I better not be dividing by 0 when I use this formula, right? If AD minus BC were 0, I'd be dividing by 0 there. This formula wouldn't work. AD minus BC is a very special number for 2x2 matrices. It's called the determinant of that matrix. And if it's 0, the inverse matrix does not exist because you'd be dividing by 0 there. But if it's not 0, then the inverse matrix does exist and it equals this. Swap the numbers in the main diagonal. The main diagonal is always from upper left to lower right. Negate the numbers on the off diagonal. A3 minus 2 is 1. 1 over 1 is 1. This is fairly simple. And this actually should look familiar if you think about our answer from the previous page. Look at those numbers. 3, -1, -2, 1. 3, -1, -2, 1. Not a coincidence. So now to finish the problem, to solve for x and y in terms of u and v, you use this product, A inverse times u. So in vector form, the vector whose components are x, y is A inverse times u this matrix 3, -1, -2, 1 times the vector whose components are u and v. And if you do that multiplication, you get 3u minus v and -2u plus v. Same answer we got before in vector form. Okay. This works with bigger matrices, with bigger systems of equations when the inverse matrix exists. But once you get past 2 by 3, well, even when you get to 3 by 3, it gets to be kind of a pain to find the inverse matrix. And you never in your life want to find the inverse matrix of, say, a 6 by 6 system or bigger, okay, by hand. And maybe never even 5 by 5, or maybe even never 4 by 4. 3 by 3 is like the biggest you want to do by hand. Matrix operations with bigger matrices do get to be a big pain. You definitely want technology to do it. In fact, technology even has trouble once you're to like 20 by 20 or bigger. Technology really bogs down. There's a branch of something called numerical analysis, called numerical linear algebra, that delves into trying to solve really big systems of equations, so like with hundreds of variables and hundreds of unknowns, which do come up in industrial applications. My teachers always emphasize this, so I'll emphasize like this to you. Oil companies, for example, they have their algorithms. They have to solve systems of hundreds or thousands of equations and thousands of unknowns efficiently somehow with their technology. And yeah, so you need other methods that somehow take advantage of special forms for special systems. It's a difficult thing.